Hello, Chem 115 students. Trying to get my recording started here with a little bit of a glitch. We need to give you some extra information about some things from the beginning of Chapter 8. The states of matter and their changes. The discussion with the intermolecular forces will come during class time in Chem Activity 27. And some discussion about pressure units has already been given in class previously. So those two are already done. Trying to get my pen started. Okay, so the goals from the chapter include these, and so the one we'll be discussing, I'll be working on here, is describing how scientists explain the behavior of gases, including the assumptions of the kinetic molecular theory. The states of matter aren't so tricky, but it's worth a few moments of conversation here. Presumably you've heard about solid, liquid, and gas from earlier pre-college education. Three states of matter differ in their way you see them, what fills the space, how orderly they are. But the primary thing that we're working to develop in our ideas in this chapter is to realize that the relative strength of attractive forces between the particles compared to their kinetic energy is going to be very different for the different phases of matter. In other words, the solids are very orderly and they have lots of attractive forces between them. The gases are very disordered and they don't have effectively any attractive forces between the particles because of their high energy. When matter is transformed from one state to the next, phase changes occur, or we also call that a change of state. Those are physical changes. Every time a change of state takes place, generally these are considered to be reversible things. They have delta G values, a free energy change associated with them. As described in Chapter 7, delta G is calculated based on an enthalpy change, which is the heat energy change, delta H, the entropy change, delta S, and it depends also on the temperature. So this equation shown here for delta G uses those three values to calculate delta G. So delta H is a measure of heat absorbed or released for exo and endothermic reactions. I said that backwards. Absorbed is endo and released is exo. And delta S is a measure of change of molecular disorder. In other words, the greater the randomness, the increase in randomness is a positive value for delta S. The bottom line is we're looking for simply the value, the sign on delta G to tell you whether or not something is going to be spontaneous, and therefore it is very much related to the temperature of the process that's in the equation here. So another piece to understanding phase changes is representing it with this type of a graph that shows low energy to high energy and how heat is added or lost from one state to the next. It makes sense if you think your way through it, but it might not have occurred to you directly. So when you think about going from a solid up to a liquid, the process is called melting, and certainly it requires heat to do that. Likewise, it requires heat, absorbing heat, to take a liquid to a gas phase. That's called vaporization, could be boiling. And each of these has endothermic, as in delta H greater than 0 type of processes. The reverse processes have the opposite signs. When you condense a gas and cool it down to make a liquid, you release heat, and for that process, delta H therefore is going to be less than 0. You are losing heat, slowing molecules down. The same will also apply for the process of liquids being cooled down to freeze them to a solid. Again, you have to lose heat, so delta H, again, the heat change is less than 0 for those processes. Okay, now the process of sublimation, where heat is absorbed, is the reverse of deposition, where heat is released as well, as shown on the right side of the screen. At each of the phase change points, the transitions between states of matter, we have some equilibria occurring, and it's not something that necessarily is obvious to you, so it's worth pointing it out. When you are at a melting point, the solid and liquid are in equilibrium. So at 0 degrees Celsius for water, oops, I forgot to turn the pen on again. The 0 degrees Celsius, the water, liquid and water as a solid are in equilibrium. Some is going each direction at all times until you finally add enough heat to convert all of the molecules to a liquid. At the boiling point, all of the temperature at which gas and liquid are in equilibrium, you have liquid turning into gas and gas turning into liquid, and if you're heating it until all of the molecules have converted to the gas phase. It's interesting to think about it that way, but we don't always realize. So if you think about ice and water in your glass, there's some ice converting to water or some water converting to ice. If the temperature is being added, like your glass is sitting out at room temperature, heat is being added and gradually all of the ice will melt. Until it does all melt, the solid-liquid equilibrium effectively keeps the temperature steady at 0 or close to it, the equilibrium temperature, the melting point. Sublimation is, of course, the change of a solid to a gas without going through the liquid state. This is characteristically known to be the case for dry ice. And if you in lab you've seen dry ice that goes from a solid to a gas without making a puddle, as I say, which is why you call it a dry ice. And so it requires also an addition of energy. The states of matter, solid, liquid, and gas, differ in how compressible they are, and we're looking at all the 3 states of matter to some extent in Chapter 8. And gases can obviously be quite easily compressed compared to a liquid or a solid. All right, what else do we need to know then about the way gases behave? And this is primarily described in a set of tenets called the Kinetic Molecular Theory. They are used to explain the behavior of gases, and they are fairly reliably used. A gas is consisting of a lot of molecules or atoms moving about at random with no effective attractive forces between them. It could be atoms if your gas is something like helium. It would be molecules if it's something like oxygen. And so there's various examples of what things are gases. And there are essentially no attractive forces between them. That's one of the theories we use to understand the way gases behave. Effectively, they're very far apart, so one molecule can't attract the next. We will be discussing attractions between molecules in class later. The second idea in the kinetic molecular theory is that the energy of a gas molecule is proportional to the Kelvin temperature. So it's written like this: energy is proportional to temperature. So the higher the energy, the greater the temperature, or vice versa. The higher the temperature, the more energy the molecules have. And so therefore, as your gas warms up, they have more energy. All the gas particles have lots of energy in a general sense. The third and fourth properties in the kinetic molecular theory are these. The amount of space occupied by the gas molecules or particles themselves is much smaller than the amount of space between the molecules. Therefore, a gas is mostly empty space. And so mostly empty space allows for gases to be compressed. The last property then is kind of an interesting one, but it's more physics related than you might care to describe. But when gas particles collide with one another, they bounce off of each other or off the walls of the container with what are described as elastic collisions. In other words, they don't just crash into the walls or each other and then stop. They crash, bang into one another with collisions that are described as elastic and bouncing back with exactly the same amount of energy. That is not a complex description, but it's one way of describing how gas particles behave, and to realize that their energies do not change because of the fact that they're bouncing about in a container with one another or into the walls. So how are these ideas in the kinetic molecular theory helpful to us? It has to do with how we describe an ideal gas. An ideal gas is one which obeys these ideas, the assumptions that are set forth in this kinetic molecular theory of gases. In reality, we live in a real world. No gas is ideal. But in practical matters, it turns out that most gases will behave as though they are ideal unless the conditions are such that they don't obey those 4 concepts. What conditions would it be then where gases are not going to behave as though they're ideal? One of them is at low temperatures. If the temperatures are really low, the gas particles slow down, they're probably going to get closer together, then they begin to have attractive forces, and, well, eventually they turn to liquids. So they are not going to behave as though ideal at low temperatures. So remember when you were using liquid nitrogen in lab and how the gas molecules in a balloon collapse rapidly when they're in low temperature and they're no longer a gas, but they turn into a liquid. That's a good way to think about it. Another example, what else can there be that causes a gas to be less ideal? Well, one to think about is high pressure. So again, it's similar to what happens when you're in a cold temperature if you put it under high pressure. So think of compressing a syringe or a tire pump or something like that where the gas molecules are being squeezed down inside a container. Then there's high pressure exerted on the gas particles. They will effectively become closer together. They begin to have attractive forces, and again, the same thing will eventually happen where the gas is no longer behaving as a gas, but instead will convert to a liquid. Okay, those are a quick summary of those concepts for this first part of the chapter. I hope this little discussion is helpful to you.